Hello everyone. Let's go over certain topics or few topics related to project management. Okay, so we'll consider one example and then that's going to touch on three topics here, right? It's going to touch on drawing the network, critical path method, and dealing with probabilistic time estimates. Okay, so it will deal with all three considering the same problem, all right? So then here is a question, we will start with the information related to certain activities A to J, right? So these are activities A to J. And what they have here is they are trying to move an office from one building to another. Between a little break they have, the break they have between the end of the summer term and the start of the fall term. So they have 3 weeks between summer and fall, and they want to make that move in those 3 weeks, right? And these are the activities that needed to be done to make the move, okay? So here they are saying that activities A, B, and C, they can start by their own because they have no predecessors, right? For example, then activity G, it has 3 activities in here. To start activity G, you must have B, C, and E finished before you start activity G, okay? So that's how you read these activity predecessor relationships. And what we'll do is we'll draw the network using activity on node convention, okay? All right, so A, B, C can start by themselves, right? So here are A, B, and C. Next, for D to start, A must be done. D comes after A, right? So here is D after A. E comes after D, okay? So here is E after D. F comes after B and E, okay? So here is your F after B and E. G comes after B, C, and E, right? So then B, C, E, they all go into G, okay? B, C, and E. H comes after F, okay? So that's H. I comes after G, okay? And J comes after H and I. So that's your project, all right? So this is the first thing, you'll have a question on the exam which will ask you to draw the network using activity on node. So that's what you do, right? They will give you information as you see in the table and you use that to draw the network, all right? So now let's proceed to the next part here. Now what you have here is they have given you 3 time estimates for every activity. So let's consider D as an example. What they are trying to say is, there are 3 time estimates. So let's understand what those 3 time estimates mean. Time estimate A is referred to as the optimistic time estimate, right? So the way you interpret this is, if everything goes well with activity D, then the project or activity D could be finished as soon as 1 week, right? So that's the interpretation of time A, right? That's the interpretation of A, which is referred to as the optimistic time estimate. On the other hand, if everything that could go wrong does go wrong, then activity D might take as long as 4 days to be over. Okay, so all the time estimates here are given in terms of days. And then the M, right? M starts for the most likely time estimate. So they are saying that generally, most likely, activity D usually takes 3 days. Okay, so those are your 3 time estimates. Optimistic, most likely, and pessimistic. And what we do is we find what we refer to as the expected time for every activity. So here is the formula for finding expected time for activity D. A plus 4M plus B over 6. So I'm going to put the numbers in there and find the expected time, right? So A is 1, M is 3, B is 4, right? So I put the numbers in there, work that out. The expected time then is 2.833. Okay, and then there is another parameter associated with these 3 time estimates. This is called a triangular distribution. Okay, the another parameter is the variance of the activity. So the variance for activity D would be B minus A over 6 whole squared. Okay, I will put the numbers in there, and then that gives me the variance of activity D. I find that the variance is 0.25. All right. So I'm going to do the same calculations for all the activities here in the table, and I will show you the table with all the time estimates for expected time and variance, right? So that's what this is. Okay. These estimates that we found for D, 2.833, right? That's right here. The variance for activity D is 0.25. That's right here. All right, and you do that for every other activity, you will get all the information that you see in this complete table. All right, so next what we are going to do is we are going to use these time estimates in the project to do the critical path method. Okay? All right, so then here is the project. Okay? And I'm going to use, as I said, I'm going to use these time estimates in the project to do the critical path method. Okay, so that time estimate for activity B goes in the circle or node for B, right? For activity G would go in the node for G, and so on for every other activity in the project. So then here are your various time estimates on the node or on the circle. All right, so that's the time estimate for B, that's the time estimate for G, and so on. So then using these time estimates, now we'll do the critical path method. Okay, so here is your network. And the critical path method, we are going to do the forward pass and we are going to do the backward pass. Right? So in the forward pass, we find 2 time estimates. We find early start right, and we find the early finish. For all the activities that you see here. Okay? So let's start with activity A. Activity A doesn't need anything to start. It can start by itself. So the earliest activity A can start would be 0. Okay? And the time estimates, I would have loved for the time estimates to be integers, but we have decimals here. But that's fine, we can deal with decimals too, but it would have been simpler if we had only integers. But that's as I said, that's no problem. So activity A can start by itself. Activity A will start at 0. It takes 3 days. So the early finish for activity A would be 3. Same for B. B will start at 0, takes 3.167, so it will finish by 3.167. Similar with C. Okay? Now D can start as soon as A is done. Right? A is done at 3, so early start for D would be 3. At the time for D, which is 2.833, you will get the early finish for D. Right? Moving on to E. E can start as soon as D is done, right? So E can start at that time. It takes 5 days. Add that. The earliest E would be finished would be this. Moving on to F. Okay. For F to start, E must be done and B must be done. B is done at that time. E is done at that time. Okay. But the earliest that both of them are done is right here. The earliest that both of them are done is 10.833. So then the earliest that F can start would be 10.833. Okay? At the time for F, you get the early finish for F. G can start after 3 activities are done, B, C, and D. the earliest that all three are done, the earliest that this is done, and this is done is again that, right? So then G similarly will start at 10.833. At the time for G would be finished by this time. H can start after F is done, right? H takes 3.833. At that time, H would be finished by that time. I goes after G, okay? So that's early start for I. At the time for I would be finished by this time. J can start after both H and I are done. The earliest that both of them are done is this, right? So then J can start at this time. At the time for J would be finished by this time, right? And that's your entire project. So now let's go backwards. Going backwards, you want to find late finish, right? So now you are going to find late finish and you are going to find late start. Okay, we'll find late start and late finish. So the latest that J must be finished is this. If it takes any longer for J to finish, then we are losing some time somewhere, right? So the late finish for J would be that. Subtract the time J takes, you will get late start for J. Okay? So now if J must start at that time, if J must start by this time, then H and I must be finished by that time. Okay? So the late finish for I would be that. Subtract the time for I, you get the late start for I. Same thing for H, right? H must be finished no later than 20.833. Subtract the time for H, you get the late start for H. So G, I must finish then. So if I must finish at that time, then if I must start at that time, right? If I must start at that time, then G must finish by 16.667. Subtract the time for G, right? That's what you get. Looking at F, if H must be starting by this time, then F must be finished by that time. Okay, so this is the late finish for F. Subtract the time for F, you get late start for F. Now looking at E. Okay, so two activities depend on E. F depends on E, G depends on E, right? F must start no later than that, and G must start no later than this. Okay? So if you don't, if you want to not to delay the project, then you cannot afford to delay either of these two. So that none of that gets delayed, right? Then what that means is E must finish at that time so that both F and G are not delayed. Okay? So then late finish for E would be that. Subtract the time for E, you get the late start for E. Looking at D, if E must start at 5.833, that's when D must finish. Subtract the time for D, that's the late start for D. Looking at C, if G must start at that, then C must be finished by that time. Okay? Subtract the time for C, right? You get late start for C. So looking at B now, B depends on, there are two activities that depend on B. F depends on B and G depends on B, right? So that none of that gets delayed, right? You cannot afford to delay F, you cannot afford to delay G. So then if G must start at 10.833, then B must finish by 10.833. Subtract the time for B, you get the late start for B. Finally, looking at A, if D must start at 3, then A must finish by 3. Subtract the time for A, and that's the late start for A. That completes your backward pass. And this is your entire critical path method, right? The critical path method protocol applied to this particular project. So now what I want to do is I want to find activities that are critical. So the activities that are critical here are the ones which have the same time indices, right? So for example, for activity D, these early start and late start, they are the same, which means D is critical. The same thing with the early finish and late finish, they are the same, and for that reason D is critical. Okay, so now I'm going to scan all the activities in the network and I'm going to select the critical activities one by one. So activity A is critical because both the time estimates are the same. Okay. Next I see, as we said, D is critical. Okay. E is critical. Then I see that G is critical as well. The next one I see here is I. And finally, J is critical. So these are our critical activities. And then when you join the critical activities, you get what we call the critical path. So this is your critical path, right? So your critical path is A, D, E, G, I, and J. Okay, so that's your critical path. A, D, E, G, I, J. So you're going to have one question separately on that, on the exam. They will give you a project network and they will say that, well, do the critical path. So you do the forward pass, you do the backward pass. Okay? So now let's move on to the third type of question that you see on project management, which is to deal with probabilities associated with project completion times. All right? So let's see how to deal with that. So here is the same table, right, we had previously. We previously found the expected time and the variance. And what I have done here is I have highlighted the critical activities in red. Okay? And what they are asking us to do is they are asking us to find a probability that the project would be finished in 3 weeks or less. Remember, they are trying to do this in the 3 weeks break they have between the summer term and the start of the fall term, right? So they want to see how likely it is that they would be able to finish this project in those 3 weeks that they have in the break, okay? So the first thing you do is you add the expected times on the critical path, all right? So I'm going to add these expected times on the critical path. So I'm going to take the times in red for the activities A, D, E, G, I, J, and I'm going to find the expected time of completion for the project. Right? I do this, I find that the expected time to finish the project is 23 days. Next, I'm going to add variances on the critical path. Okay? So then here I am adding the variances on the critical path. I see that the variance of the critical path is 2.888. So then what will be the standard deviation? Standard deviation is always the square root of variance, right? So I'm going to find the standard deviation, or I'm going to find the square root of the variance, and I see that the standard deviation is 1.7, right? So these are the basic calculations. All right, so now what does this expected time of 23 days mean? Okay, so remember, this is an estimated time. Because we are not in a single time scenario. You have 3 time estimates here. You have AM, A, M, and B, right? And from that, we came up with this expected time. So you cannot talk about certainty of project completion in 23 days. You can only talk about the probability of project completion in certain days, in some days, right? And those days are 3 weeks here. So what does those 23 days mean? 23 days means that the project is expected to be finished within 23 days, right? But this time estimate of 23 days is distributed by a bell curve. Okay, so then here's the bell curve. The expected completion time for the project is 23, but the project might be finished sooner, the project might be finished, the project might take longer, all right? And what we want to do is we want to find a probability that this would actually be finished in 3 weeks or less. So 3 weeks means how many days? 7 days times 3, it means 21 days, right? So what we want to do, okay, so the expected time 23 is distributed by a bell curve, okay, and we want to find a probability that the project would be finished in 21 days or less. So we want to find that area of the bell curve, okay. All right, so next, to find that area of the bell curve, you need to find the value of z associated with the probability that you want to find. You want to find a z value for 3 weeks or 21 days. So then here is the formula for z, okay, x minus mu over sigma. So mu is the average of the bell curve, which is that. Sigma is the standard deviation of the bell curve, which we found on the previous slide, all right? And x is the time that you are interested in, which is 3 weeks or 21 days, right? So I'm going to put those numbers in the formula there, okay? So these are the numbers. We found earlier standard deviation was 1.7, right? So you work that out, you get the value of z equal to minus 1.18. So now you need to look up the normal table, okay? So then here is the normal table that is given in the book. And what you do is you look up a value of minus 1.18. Now the normal table does not deal in negatives. It deals only in positives. So we'll look up a value of z equal to 1.18. And normal curve is symmetric, so negative 1.18 is equal to positive 1.18 in terms of probability. Okay, so here is the bell curve then. We want to look up the value equal to 1.18. So you will essentially look up in the row 1.1 and in the column 0.08. All right. So that gives you the area equivalent to the value of z equal to 1.18. So this is 1.18. That's how that works, right? So then that area is right here. And you will see that this area of the bell curve is actually equal to 0.3810. Okay, now let's go back to the chart that we had earlier. All right, 0.3810, we'll keep that value of the area in mind, 0.3810. Okay, so here is your chart. And the way this bell curve, is arranged, or the normal table is arranged, is when you look up a value, it gives you the value between whatever z you are interested in and the average of the bell curve, right? So that's the area you get. So that happens if it's positive z. If it's negative z, then it's giving you value to the left of the bell curve, right? So that's what you get if z is negative. In our case, z is negative. Z is minus 1.18, right? So that's z, minus 1.18. So the way, we got 30 at 10. So 30 at 10 then is this area, okay? And what you want to do is you actually want to find the project would be finished in 21 days or sooner. So you are interested in this area of the bell curve, okay? So we looked up in the table, right, normal table, we found that value. That value we found is equal to 0.3810. So then what is the value that we want, right? Now remember, bell curve, the average of the bell curve splits the bell curve into half. So what that means is this entire region is 0.5, right? That whole thing is 0.5. So this whole thing is 0.5. And we are only interested in a portion of this, right? We don't want that. So we don't want this region, but we want the region to the left of this, okay? So the way you want to find this is, right, you take 0.5 and you subtract the area shaded in blue and you will get the area that you want, okay? So this is the answer then. So that whole thing is 0.5 and your answer is, you take that whole thing, right? You take this whole thing and you subtract this portion from there, and then that gives you the area that you are interested in. That will give you this, and this is what you want. You want the probability that the project would be finished in 21 days or sooner, right? So you essentially take 0.5, you subtract the shaded region, and you find that the probability that the project would be finished in 21 days or sooner is 11.9%. Okay? So that's the third type of question you can get on exam based on probabilistic time estimates. And then there are other interpretations that you should be able to draw, you know. So for example, then what is this shaded region, right? What is that? Okay? So let me clean this up a little. So we did all this, right? So that area is 0.3810. So what does that represent, right? So the way to interpret this is that is the probability that your project would be finished somewhere between 21 days to 23 days, right? So that's the answer. You know, what is that area? That area is the probability that it will be finished between 21 and 23. And our question is, we want the area that it will be finished in 21 days or sooner. So essentially we took that 0.5, subtracted 3810, and you know, as we discussed earlier, we found that the answer to that question is 11.9%. All right? So that is all for this lecture, right? There are several problems in the book. At the end of the chapter, solve as many as you need to feel comfortable with this stuff, okay? So good luck with your preparations, and thank you for all the attention.